Hello students, welcome to Unacademy Studios Bridge. This is the second lecture. This is the second part of slope and deflection cantilever beam. If you have already not watched the first part, then I must request this to you that you first go back and you first watch and complete the first part, which you will find on the same channel as part 1. Slope and deflection cantilever beams. So because we have already discussed about 4 different type of problems, if you noticed carefully, my dear friends, in the very first session I told you that there are 5 different type of problems possible as far as cantilever beams are concerned. So now in this second part we will discuss about that 5th variety of problem. Alright. But before we do that, those of you who are new to this session, let me very briefly introduce myself to you. I'm Marut Tiwari. I did my engineering from Lucknow and masters from IIT Kharagpur. I've been a recipient of multiple awards at IIT Kharagpur, Institute Silver Medal and IIE award with a CGPA of 9.63. I have cracked GATE multiple times. And I'm also an author of a comprehensive GATE book, that is GATE in 75 Days, which is one of the best sellers in this segment. So this is all about me. I'm currently associated with Unacademy, and Unacademy is having a pool of outstanding educators out there. And this is probably the best thing about Unacademy, that you can access a lot of courses and number of educators are there, so you can switch between the educators, you can opt for courses of your choice, you can, a lot of flexibility is there. And this is, as I said, a lot of reasons I can give you to join Unacademy for your preparation of GATE and ESE. One reason, in my view, in my perspective, one reason is the flexibility. And of course, the second reason is that you get a lot of things for free. Like just like you get a lot of demo classes or something in some institute. Similarly, here you get a lot of plus package out there for free. And then other advantages that are there are, number 1, totally flexible schedule. It is up to you that whether you are going to take fluid mechanics first and strength of materials second, or you're going to take a strength of materials first and thermodynamics second, or you're going to take production first and heat transfer second. Like it's up to you that how you are going to sequence the subjects and the courses out there. You can watch the lectures in English, you can watch the lectures in Hindi. For example, the same thing that I'm going to teach you now in English, the same thing I have already I've already recorded in Hindi. So part 2 Hindi is already available. It has already been uploaded on the same channel. Now I'm recording the same thing. I'm premiering the same thing in English. And of course, one big advantage is that you can do unlimited practice. Like there is no limitation as to how many times you're going to watch the same thing. It's like Prime Video or Netflix subscription, that once you take the subscription, you watch it as many times as you want. Alright, it's not like one-time movie ticket or something. So guys, a lot of flexibility, a lot of convenience, a lot of freedom. You can watch and you can learn anytime and anywhere. So there is as much flexibility and as much convenience as there can be, but at the same time you feel it like a real classroom coaching scenario. Why? Because you can, in the real time, you can ask anything to the educator and educator can see it, and educator is going to give you the response in the real time. So it feels like a real practical class out there, and educator is going to ask number of questions in the Unacademy Plus classes. So you can just reply to them, you can just respond to them. So it's a win-win situation for the students. Why? Because one, they have enough flexibility to cope up with their colleges, cope up with their jobs, part-time jobs or whatever, and at the same time to get a real practical classroom like environment. Alright, It's very easy, my dear friends. It's very convenient. There are, again, it's a flexible thing. Unlike conventional classroom coaching programs where you have to pay one entire hefty amount in one go, here you can go for flexible, convenient packages out there. You can go for monthly package, you can go for 3 months package, you can go for 6 months package, you can go for 12 months or 24 months package. 24 months package is the most cost effective package. Why? Because 40,000 is the total package cost, and if you divide it by 24, you get, though you have to pay as a one-time fee, but my dear friends, effectively you pay just 1667 rupees per month. Like, this is one of the most cost effective learning that you can have for GATE. All right, particularly if you compare with the quality of educators. Like, the quality of educators, there is no compromise, but at the same time you're getting the same thing, the similar quality as you get anywhere else in, let's say, 70-80K. You get the similar quality and similar problems, practice and everything at just 1667 rupees per month effectively. In fact, it can be brought down even further. My dear friends, you can use my code MTLive, and if you use my code MTLive, then this package cost 40,000 comes down to just 36,000. So 36,000 divided by 24 is nothing but just 1500 rupees a month. It's my dear friends, nothing more than a moderate normal tuition fees or something like that. I mean, 1500 rupees per month would be the travel expenses if you join a conventional classroom coaching program. All right, 1500 rupees per month would be the travel expenses, and here you can do everything from your hostel, from your room, from your flat, from your home. All right, so guys, this is probably the most cost effective thing that you can have as far as your GATE preparation is concerned. Now, similarly, for 12 months package, the overall cost is 25,000, and if you divide that 25,000 by 12, effectively you get to pay just 2,083 rupees per month effectively. And as I said, it can be brought down even further if you use my code MTLive at the time of subscription. Then, my dear friends, the total package cost comes down to just 22,500 rupees, and this is effectively less than 2,000 rupees per month. Less than 2,000 rupees per month. Now, if you compare, I say it again, if you compare this with hefty fees and travel cost and hostel cost and fooding, lodging, everything, then you'll find out that this is probably unprecedented, and this is probably the win-win situation, the super win situation if you're going to prepare for GATE. And educators like me are there on Unacademy, and I assure you that I'm going to take 3, 4, 5 subjects out there with similar quality and similar intensity and similar in-depth problems practice. All right, on Unacademy Plus, I'm going to take number of courses out there, and I'm going to teach each and every concept with the very basic and up to a very advanced level. All right, starting from the very basic level and up to a very advanced level, and I'm going to cover variety of problems, so many problems I'm going to cover that, my dear friends, not even one type of problems would be missed or would be left out there. And at the same time, you're also going to enjoy the learning of engineering in a true sense. So it's very easy. All you need to do is you need to go to Play Store and you need to open Unacademy Learning app and install that Unacademy Learning app. After installing that Unacademy Learning app, you need to choose GATE as your goal. And after choosing GATE as your goal, my dear friends, you're going to have a lot of subscription packages out there, and with these subscription packages you can go ahead and you can have a very good learning of GATE. So now let us start learning about the next part of cantilever beam problems. My dear friends, if you have watched part 1, then in the part 1 we have largely used, this one method that we call by the name method of superposition, isn't it? In part 1, we have largely, to solve every single type of problem, we've largely used the method of superposition. That 4 standard cases were there. And if you remember the formulas of each and every standard case, then any given beam, any given typical problem can always be broken into those standard beams. And then if you remember the formulas of standard beams, then you can simply superimpose them. But now I'm going to tell you about one more method. Why? Because few type of problems, few variety of problems in cantilever cannot be solved using superposition. What kind of problems cannot be solved using superposition, or what kind of problems will be solved easily maybe using yet another method that we'll discuss very soon. Don't worry. Don't you worry. Alright, don't you worry. Don't you have an iota of any fear or something? I'm going to describe it all. But I say it again, if you have not watched part 1 of this series, then please go back and first you complete the part 1 as quickly as possible. And then you come to this one and then you can watch this one, because this is in continuation. And in continuation, you are going to learn it very well. So if you have not watched part 1 yet, please go back and first watch it and then come back to this one, because this is a continuation for that. And guys, in that part 1 we have used largely to solve every type of problems, we have used method of superposition. If you remember, in part 1 we have discussed about 4 type of problems. Type 1 problems based on standard beams, type 2 problems based on combined loads, maximum slope and maximum deflection, combined loads, and they are asking maximum slope and maximum deflection. Type 3 problems where we discussed about calculating theta intermediate and y intermediate, and type 4 problems we discussed about propped cantilever. Today we are going to discuss about yet another variety, but before we discuss about that yet another variety, let me just tell you about one more method. And this one more method is known by the name moment area method. This one more method that we are going to use for the other variety of problems is known by the name moment area method. Moment area method, my dear friends, has got 2 theorems. Moment area method has got 2 theorems. I'm not going to derive these 2 theorems because only roughly 60 days are left as far as GATE is concerned. So let's be straightforward. Let's go ahead directly and attack the problems. Let's try understanding that how problems are attacked, how problems are solved. Theorem 1 says that if you have 2 points P and Q on the beam, then the slope difference between Q and P is gonna be equal to area under bending moment diagram between these 2 points P and Q, and this divided by EI. This is theorem 1 of MAM. This is theorem 1 of moment area method, and in short I'll call it MAM. So MAM is going to help you a lot. Alright, in certain kind of problems. Theta Q minus theta P is equal to area under bending moment diagram between P and Q divided by EI. Alright, but there is one more way to write the same thing. Sometimes we'll take this EI into the bending moment diagram itself and we'll construct a new kind of diagram that is called M by EI diagram. So rather than dividing EI separately, we'll divide by EI values in the diagram itself, and we'll construct a modified bending moment diagram. That modified bending moment diagram will be known by the name M by EI diagram. Alright, that will be known by the name M by EI diagram. This will be needed whenever you have EI variable. Alright, if you have EI value variable, then we'll require this. This another technique, area under M by EI diagram. Now, what is the second theorem? The second theorem says that if you have a point of zero slope, available on the beam, then with respect to that point of zero slope, my dear friends, with respect to the tangent of point of zero slope, the deflection at any other point, but mind it, the second theorem is valid only when your reference is available at point of zero slope. Please keep this in mind, my dear friends. That second theorem that I'm going to tell you would be valid only when you have the reference point available at point of zero slope. Alright, so what is the second theorem? The second theorem is that if you have point of zero slope available, then with respect to the tangent at that point of zero slope, the deflection is going to be, if you have point of zero slope available, then with respect to that point of zero slope, the deflection at any point is gonna be area under bending moment diagram between these 2 points P and Q multiplied by x bar measured from Q, wherever you are finding out the deflection, divided by EI. And as I said for the theorem 1, as we have already discussed about theorem 1, similarly for theorem 2 also, just in case if the beam has variable flexural rigidity. Now, what is a variable flexural rigidity? We'll talk about it. Don't worry, we'll solve a problem like that in the upcoming 10 to 15 minutes. So guys, what is a variable flexural rigidity? What is a variable EI value? We'll know that. Don't you worry. Alright, just keep listening and keep absorbing these two theorems. Theorem 1 is the difference of slope. The difference of slope between any 2 points is equal to area under bending moment diagram, or maybe area under M by EI diagram. Second theorem says that if you have point of zero slope available, then with respect to that point of zero slope, my dear friends, the deflection is gonna be area into x bar divided by EI, or maybe if EI is varying, then we'll construct M by EI diagram, and rather than considering bending moment diagram, we'll take area under M by EI diagram, and then we'll multiply it with x bar. Please keep these two theorems in your mind to solve remaining type of problems in cantilever beams. I say it once again that we have already solved 3 type of problems in cantilever beams. Sorry, 4 type of problems in cantilever beams we have already solved, and now we are going to continue with the other type of problems. In fact, we are going to continue with type 4 problems only. In type 4 we have already discussed about, in type 4 in the previous part of this lecture, we have already discussed about, my dear friends, one indeterminate beam that is known as propped cantilever. But now we are going to discuss about another indeterminate beam, and this another indeterminate beam based on cantilever is known by the name fixed beam. This another indeterminate beam is known by the name fixed beam. A fixed beam is something that will have a fixed support, at both extremes, and maybe in between it is going to have some load. Now this is what you call fixed beam. Why fixed beam is an indeterminate beam? Let's talk about it, that why fixed beam is an indeterminate beam. Why do we call it indeterminate beam? Because, my dear friends, you got to have one unknown reaction force and one unknown reaction moment at P, and similarly you got to have one unknown reaction force and one unknown reaction moment at this point Q here. Alright, at this point Q here, you'll have one unknown reaction force and you'll have one unknown reaction moment, isn't it? So this is what we have. Now, reaction force is something that people easily understand, but they don't, sometimes they get confused that where I have to introduce this reaction moment. Because reaction force, RA, RB, RC, RD, RP, RQ, every single time at any support you introduce R. You introduce R at any given support. But when do we introduce M? When do we introduce this reaction moment out there? Let me tell you about this, guys, that as far as a fixed support is concerned, a fixed support is not only going to resist to a force, a fixed support is also going to resist to a moment. If it is a hinge, it is not going to resist to the moment. If it is a hinge, then about the hinge, the body is going to rotate. About the hinge, if you are supporting something at hinge, then my dear friends, the body is going to rotate like this. It is going to rotate like this about a hinge. But about a fixed support, no matter what is the load acting at the beam, about a fixed support, it's not going to rotate anymore. No matter how much force you apply, the fixed support doesn't allow the rotation, and therefore fixed support is resisting the moment also. Fixed support is resisting the moment also, and therefore whenever you have fixed support, you're going to introduce not only a reaction force but also a reaction moment. Alright, now you have 4 number of unknowns available here. 4 number of unknown reactions available here. What are these 4 number of unknown reactions? These 4 number of unknown reactions are RP, RQ, MP and MQ. What are the equilibrium conditions available? Equilibrium conditions, my dear friends, we have sigma Fy is equal to 0 and we have sigma M is equal to 0. Now you see, you have 4 number of unknowns but only 2 equilibrium conditions. So equilibrium conditions become insufficient to determine the number of unknowns, and that's why we call such beams as statically indeterminate beams. Alright, so how do you solve it? Now it's very natural that unknowns are 4 and equilibrium conditions are 2. So we need 2 additional conditions. From where we are going to get those 2 additional conditions? It's very easy. At a fixed support, rotation is not allowed. So theta P is 0. At a fixed support, rotation is not allowed. So theta Q is 0. Alright, theta P is 0 and theta Q is 0. Now you think about the theorem 1 we have discussed just now. Think about theorem 1 of MAM that we have discussed just now. Theta Q minus theta P is equal to area under bending moment diagram divided by EI, isn't it? Now theta Q is 0 and theta P is 0. Theta Q and theta P both are 0. On the right hand side we have what? On the right hand side we have theta Q minus theta P is equal to area under bending moment diagram divided by EI, isn't it? So theorem 1 is already there with you, and please do remember this theorem because this theorem is something that you're going to need now to solve fixed beams. If you recall in the previous part of this lecture, we have already learned how to solve propped cantilever beams. Alright, but for fixed beams, I'm going to tell you a newer and quicker trick. Please don't try solving fixed beams using superposition. Why? Because superposition is usually going to result into lengthy procedure as far as fixed beams are concerned. So guys, we have theta Q 0, theta P 0, and then we have area under bending moment diagram between P and Q divided by EI. Now because theta P is 0, theta Q is 0, so we get total area under bending moment diagram. Total area under bending moment diagram must be equal to 0. This becomes one important condition for solving fixed beam problems. And please keep this in mind, okay? Please keep this condition in mind. This is going to help you in solving any fixed beam problem out there. Now let us use the second theorem. Now let us use the second theorem. The second theorem is what? The second theorem is YQ is equal to area under bending moment diagram multiplied by X bar. The second theorem is YQ is equal to area under bending moment diagram multiplied by X bar divided by EI, isn't it? So this is the second theorem that we have. Now, because at Q you have introduced a fixed support. At Q you have introduced a fixed support, my dear friends. Therefore, YQ becomes 0. Therefore, let me take the second theorem. Second theorem says that YQ is equal to area into X bar divided by EI. But YQ becomes 0, and if YQ becomes 0, we have another condition available, that is area into X bar is equal to 0. Area into X bar is equal to 0. This is the second condition that you got to remember. This is the second condition that you must remember, my dear friends. These are the equations that you are going to use to solve any fixed beam problem. Please do remember both these equations. Number 1, total area under bending moment diagram must be equal to 0. Number 2, total area multiplied by X bar. X bar would be measured from any one given end. So total area multiplied by X bar, this will be equal to 0. Alright, so these two conditions you must remember, and you would be able to solve any given problem based on fixed beam. Let me take a problem. If you have attended the previous part of this lecture, then we have solved there in the previous part of this lecture, we have solved 5 problems. So in that sequence, this is going to be example number 6. As an example number 6, let's say we have got a fixed beam, and let's say this particular fixed beam, my dear friends, is subjected to a load W at 2L from one end and L from another end. If I take load W acting at the midpoint, that is going to become a very easy problem. Why? Because reactions will be simply W by 2 and W by 2, and then using any one given condition, just one given condition will give you the unknown moment value. Because symmetric beam is going to have same R and same M, so it will become very simple and very easy problem. Therefore, I'm going to take a little typical one where the load is not acting exactly at the mid, the load is shifted a little bit away from the mid position. Alright, and suppose, my dear friends, suppose they are asking you to calculate the unknown reaction force and the unknown reaction moment here at this point Q. Suppose they are asking you to calculate unknown reaction force and unknown reaction moment here at this point Q. This point is P here and this point is Q here. How you are going to solve this? As I said, though you have equilibrium conditions also available, but please do not use equilibrium conditions. Please do start with these two conditions out there. Do start with these two conditions. Condition number 1, total area under bending moment diagram must be equal to 0 and area into X bar must be equal to 0. So you got to use always these two conditions. But before we use, so what are these two conditions? These two conditions are area must be equal to 0, total area under bending moment diagram, and A into X bar must be equal to 0, isn't it? So these two conditions you'll have to use. Naturally, for using area under bending moment diagram and area under bending moment diagram multiplied by X bar, naturally you will have to first construct the bending moment diagram. But bending moment diagram you are not going to construct in the conventional way. Bending moment diagram you are not going to construct in the traditional way. My dear friends, you are rather going to break this beam into number of standard beams. For example, 1 cantilever beam subjected to simply RQ at the end, another Cantilever beam subjected to simply MQ at the end. Total length of the beam is 3L. Keep that in mind. Total length of the beam is 3L. Keep that in mind. And then there is this, at point R, there is this load W acting in the mid at point R at distance 2L. In the remaining distance L, there is nothing. So you got to draw the bending moment diagram for these individual beams. Why? Because total area under bending moment diagram will anyway remain unchanged. Total area under bending moment diagram will anyway remain unchanged, my dear friends. So let's go ahead. We have broken the beam into 3 standard beams. Let's go ahead and draw the bending moment diagram for these 3 beams. For this one, the bending moment will be 0 here. For this one, the bending moment will be 0 here, and here it will be RQ multiplied by 3L positive. RQ multiplied by 3L positive. Alright, this is sagging the beam. So here it is going to be RQ multiplied by 3L positive, and in between the bending moment is going to vary linearly. In between the bending moment is going to vary linearly. So here it is 0, and here it will be RQ multiplied by 3L, which is 3RQL, and this is a positive bending moment area. Let's call this as area number 1. In this one, in the second beam, second standard beam, you see everywhere you are going to get MQ, 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 MQ and MQ only, and therefore bending moment diagram will be simply a rectangle with the height equal to MQ everywhere and the base equal to 3L, and this is a hogging bending, so this will be taken as negative. Now here between Q and R there is no load. Between Q and R there is no load, so the bending moment will be nothing here, but starting from R it will be W into 2L. W multiplied by 2L will be the value. W multiplied by 2L, and this base is again 2L, and this is L, this is R, Q and P. Let's call this is again a negative area. Let's call this as area number 2, and let's call this as area number 3. Now before we can use these two conditions, my dear friends, we'll have to determine these areas out there. So one by one, turn by turn, let us determine these areas. Area number 1 will be half into 3L into 3RQL, half into 3L into 3RQL. Now if you calculate that, half into 3L into 3RQL, 3 and 3, 9, and RQL is square divided by 2, because half into base into height. So I'm using half into base into height. Now what about the CG of this particular area? The CG of this particular area will be available at 2/3 of 3L, and 2/3 of 3L is nothing but 2L, isn't it? And then my dear friends, we have the second area simply as MQ multiplied by 3L, but be careful, this is a negative area. And what will be the CG of this area? CG of this area will be available at half of 3L. Half of 3L is what? Half of 3L is 1.5L. Alright. And then my dear friends, we have this third area. The third area is going to be half into 2L into 2WL. So half into 2L into 2WL is what? Half into 2L into 2WL is what? 2 is a common thing here, so it will kill each other, and we are left with 2WL square. But please mind it, this is a negative area once again. So this is a negative area and it is 2WL square, and then you have x3 bar is what? L plus 2/3 of 2L. L plus 2/3 of 2L. This is the x3 bar value. Now you have A1, A2, A3 and x1 bar, x2 bar, x3 bar values. Let us use the first condition. What is the first condition? The first condition is the total area under bending moment diagram must be equal to 0 in case of a fixed beam. In case of a fixed beam, total area under bending moment diagram must be equal to 0. Now what is the total area? Total area is this one and this one and this one. So let's just sum them up and equate them to 0. Let us just sum them up and equate them to 0. This is 4.5 RQL square minus 3MQL and minus 2WL square is equal to 0. So you get, effectively you get one equation in RQ and MQ. Two unknowns are there and we want to solve these two unknowns. So we get one equation out there. Now let us use the second condition. Second condition is what? Second condition is A1x1 bar, A2x2 bar, A3x3 bar. The total first moment of the area must also be equal to 0. So A1x1 bar is what? A1x1 bar is 4.5 RQL square multiplied by 2L. Then A2x2 bar, A2 is negative MQ into 3L multiplied by 1.5L. And then A3x3 bar, A3 is again negative 2WL square multiplied by, this is x3 bar is what? X3 bar, if you simplify, you will get 7L by 3. This equal to 0. This equal to 0. You get one more equation in RQ and MQ. You get one more equation in RQ and MQ. So two unknowns and two equations, you can solve both of them. And now just in case, though they will never ask such a lengthy problem, but just in case after solving RQ and MQ, if you want to find out RP and MP also, then you can use equilibrium conditions. You can balance the forces, you can balance the moments. Alright, so guys, any fixed beam problem and you're going to solve it like this only. But I would recommend you not to waste so much of time on fixed beams. Just solve one or two sample problems for the sake of satisfaction that you know how to solve fixed beam problems. Don't practice and don't waste your time much on the fixed beams. Rather, you practice more and more problems of all the types that we have discussed in the previous part. Why I am saying that fixed beam problems need not be practiced much? Because my dear friends, you can see here I have not taken a very complicated problem and yet it is taking a lot of time. It is taking a lot of time to solve, and therefore my dear friends, fixed beam problems are usually going to be involved and lengthy problems. This is precisely the reason that they have not asked so many problems from fixed beams as far as gate is concerned. But at the same time, I must clarify that if you are preparing for ESE, if you are preparing for engineering services exam, then you must solve fixed beam problems as many as possible, because in engineering services exams they have asked fixed beam problems quite frequently. In GATE they have not asked fixed beam problems even once. Alright, in last 20 years they have not asked even one fixed beam problem. So don't practice so many problems based on fixed beam. Just solve one or two more problems. Maybe you can take UDL, maybe you can take couple anywhere, and you can try solving that problem by yourself. So guys, this is the end of indeterminate beams based on cantilever. We have already discussed about propped cantilever in the previous video. In this one we have discussed about the fixed beam. Now let me take you to the last type of cantilever beam slope and deflection problems. Last type of cantilever beams slope deflection problems are going to be based on varying flexural rigidity, that is varying EI value. How to solve such problems? To know that, how to solve such problems, to know that, my dear friends, to understand that, I'm gonna take this gate problem out there, this gate problem that they asked in 2011 for 2+2 marks. This gate problem that they asked in 2011 for 2+2 marks. Alright, so what is the problem? The problem goes like this. The problem goes like this. They said that we have got a cantilever beam with a concentrated load W at the free end. The thickness of this particular beam is remaining constant. The thickness is remaining constant, but the width of this beam is varying linearly with 0 value at the free end and maximum value at the fixed support. Alright, 0 value at the free end and maximum value at the fixed support. So this is what? This is the variation of width. This is how the width of the beam, width of the cross section of the beam is varying. Alright, and this is the plan of the beam. This is plan means it is the top view. If you're going to look at the beam from the top, then you will see something like this. The thickness from the front is a constant thing, but the width is continuously varying from 0 value at the free end to maximum value at the fixed support. This is not any shear force diagram or bending moment diagram or something like that. No, this is just the plan of the beam. Before I start solving this particular problem, they asked at any given x section, my dear friends, they asked to calculate moment of inertia value at any given x position. They asked to calculate moment of inertia value, and they asked also to calculate maximum deflection in this particular beam. This problem was asked in GATE 2011, and GATE 2011 was the year when I wrote GATE. And let me tell you this, that I solved this problem like a pro. Why? Because I knew about moment area method. Because I knew about moment area method, and I knew about, each and every type of problem, that if this type of problem is there, then I have to use this weapon. If this type of problem is there, then I have to use this weapon. So the key to crack GATE is always to identify the variety of problems. That okay, this type of problem is there, this type of problem is there, this type of problem is there, and to have a weapon ready for each and every type. That if okay, this type is going to be there, I'm going to use this weapon. If this type of problem is going to be there, I'm going to use this weapon. So always strategize your preparation in this way only. If there is a variable flexural rigidity, then you'll have to take help of moment area method. So let's go ahead and try solving it. But before we solve it, my dear friends, I just want you to visualize this, because in my Hindi lecture, Hindi medium thing of this video that I have already broadcasted, that I have already published, in comment section some students raised this doubt that the beam is triangular, why you are using moment of inertia formula of a rectangle. Let me very clearly tell this to you, my dear friends, that the beam is triangular. The cross section of the beam is not. The cross section of the beam is still rectangular, and the beam is going to look something like this. If I give you the 3D visualization of the beam is going to look something like this. Alright, now you see this beam is having constant thickness everywhere, and this beam is having variable width. So width is continuously varying and the thickness is remaining constant. Now you will say that this is still triangular only, no? This looks like triangular only. No, strictly no, sir. Beam may be triangular, but the cross section of the beam is still rectangular. And let me identify that cross section. Like at X position, you have the width, let's say beta, but at X position, the thickness is still T. Alright, here you can identify at any given random X position, the width is beta and the thickness is T. Now what is this? What is this, sir? This is rectangular or not? So if you're going to cut the beam anywhere, you will get to see nothing but a rectangle. Alright, and moment of inertia is going to be simply BD cube by 12 or BH cube by 12. Moment of inertia at X position is simply going to be beta t cube divided by 12. Now what about beta? Beta is not given in the question. In the question b is given, but you can very clearly and very easily you can relate beta with b using the similar triangle. Using the similar triangle, you have beta divided by x. Beta divided by x is equal to b divided by L. Using the similar triangle, you can see beta divided by x is equal to b divided by L. So from here you'll get beta is equal to what? From here you will get beta is equal to bx divided by L. And this is how you get, if you replace beta here, bx divided by L, then my dear friends, you get the moment of inertia value bx t cube divided by 12L. Let me tell you that this is a problem. This is a problem, my dear friends, where they rewarded 2 marks to me for only this much, for only expressing moment of inertia at any given x position. Alright, at any given x position, this is the moment of inertia value. Now at x position, what is the bending moment value? At x position, what is the bending moment value? The bending moment value is very clearly w into x. So at x position, the bending moment value is, at x position, the bending moment value is nothing but w into x. Now let us try finding out the m by ei value. Why? Let's go back and let's recall something that we have learned in this session only. I told you, my dear friends, I told you that just in case if moment of inertia of the beam is varying, then you will have to consider m by ei diagram, not just bending moment diagram. So now we'll go ahead and we'll try constructing the m by ei diagram. We'll try constructing the m by ei diagram. To construct the m by ei diagram, let us first of all find out the m by ei value. M by ei value is going to be w into x, and e is constant here. What about the moment of inertia value? The moment of inertia value is bx t cube divided by 12L. You see, x is getting cancelled here. X is very clearly getting cancelled here. And if x is getting cancelled here, then my dear friends, we get this 12L goes to the numerator and we get 12WL divided by EBT cube. And this interestingly doesn't depend upon x. This interestingly doesn't depend upon any form of x. Alright, there is no x present here. And if there is no x present here, then naturally this entire thing is independent of x. And if it is independent of x, it becomes constant. If it becomes constant, then m by ei diagram is simply going to be a constant value everywhere. Alright, simply going to be a constant value everywhere, and that constant value is 12WL divided by EBT cube. Mind it that this is not bending moment diagram, this is m by ei diagram. This, my dear friends, is m by ei diagram. Alright, why? Because we have plotted not the bending moment values, but we have plotted m by ei values. Now let us go ahead and use the second theorem. The second theorem is what? The second theorem is that yq is equal to a into x bar, area into x bar. And I'm not dividing by ei because I have already divided by ei in the diagram itself. Alright, so we have the area very easily available here. The area is L multiplied by 12WL divided by EBT cube. This is the area. And what about x bar? x bar is L by 2. Because this is a rectangular area, so x bar is L by 2 with respect to q. Now if you simplify this, you'll get the maximum deflection, which will be available here at the free end. You'll get the maximum deflection as 6WL cube divided by EB T cube. And this, my dear friends, is going to give you another 2 marks. So you see, if you know moment area method, and particularly not only, you see, in GATE, knowing each and every method is not enough. Knowing where to apply which method is rather going to be more important thing. Why? Because in the same problem, you use method A and you can get the result in 1 minute. In the same problem, you use method B and you might take even 10 minutes. So which method is to be used in which kind of problems is all about guidance. And that's why I'm here. That's why I'm here. I promise this to you, that if you keep following and if you keep, following me at both the places, on the channel Studios Bridge also, and please follow me on the Unacademy application also. All right, that information is there on the very second slide. I'm sorry. That information is there on the very second slide, that you can follow me if you just note this link out there, and if you just click at this particular link, you can follow me on Unacademy also. Keep following. I'll tell you that not only methods are main thing, but which method is to be used in which kind of problem is probably more crucial thing to know. All right, so guys, let's wind up this session for today. I hope you enjoyed the session as much as I enjoyed. Do remember, I quickly recapitulate, if it is a fixed beam problem, please do remember these two conditions: area under bending moment diagram is equal to 0 and area into x bar is equal to 0. And then, my dear friends, for variable flexural rigidity, wherever beam's cross section is varying continuously, for such problems, please do remember the moment area method only is going to help you. And using moment area method, we solved this particular problem. Thank you so very much for watching this. Like the videos so that I must be motivated to make more and more videos out there. All right, and hit the bell icon so that you get the regular notifications whenever I keep posting the videos out there. And I have made another video which you will find on this channel only. I made another video for examination schedule. Don't forget to watch it. All right, why? Because that's going to give you a boost. Just a 10 minutes video, it is there on this particular channel. And whenever you are going to subscribe for Unacademy Plus packages, don't forget to use my code MTLive, because that will fetch additional 10% discount to you. Thank you so very much, and thank you.